Hello everyone, in this video we are going to study about the next topic of the third unit, which is the shear stresses in the beams. As we know that when any beam is subjected to a constant bending moment or a constant force when that is being applied over the beam, then it results in a bending moment and shear force is zero. So there will be only bending stresses in the beam. For example, in the case of overhanging beam, when the shear force is being applied at the end support, then the bending moment is constant throughout the middle portion and shear force is zero. But such type of practice in the beam is absolute. It is very rare that when a beam which is subjected to such type of condition, only bending moment will generate. So at the same time, shear forces also generates in the beam. So let us consider a case in which we have a simply supported beam and on which UDL is being applied. We take two sections AB and CD, and we take a section EF which is at a distance of y from the neutral axis, and we will determine the shear stresses that is being applied on that portion. So taking use of the bending equation, we know that the bending stress at that portion will be equals to m over I times of y. Okay, so at the other end of this infinitely small cylindrical portion, we will have the bending stress of sigma plus d sigma. Okay, so that if we multiply that by that stress by the area, then we will get the force which is being applied on that cylindrical portion, and simultaneously we can get the force on the other end of the cylinder of the CD, which is this. Okay, so there and that both of these forces are of different magnitude. So if we found out the net unbalanced force, then it will be equals to this formula, and if we integrate for the whole section, then we'll get dm over I cross a cross y bar. So this is the total unbalanced force, due to which unbalanced for this horizontal portion which is above this EF, this moves in the other direction. So in order to keep this portion in the intact position, or equal and opposite shear resistance must get developed inside this member in order to resist that vertical moment. And if we calculate that value, that will be f times of a y bar over I times of b. So that is the shear stress that must get generated in the object in order to resist that force. So we will be using this formula in order to solve various numericals for various types of the section. Let it be I section, circular section. We will use this formula, same formula. We will just change this area and y bar value, and then we will get the multiple results from this case. Let us consider this in numerical, in which we have B and D, and the shear force is being applied. So all of these values we have just put the value, then you will get the shear stress value at a distance of y1, which is again given in the question. So just use that simple equation and you will get the multiple results in different section. If we have a rectangular section, as in this case, then we know what would be the area and the distance of the CG from the neutral axis. So if we put all those values, then we will see that the actual shear stress distribution is in a parabolic way, having maximum shear stress at the center. And if we look at its equation, then it is this equation. Okay, and if we put the value of y at the top edge or at the neutral edge, then we will find that its shear stress value at top is 0, and at the neutral axis it is maximum, which is 1.5 times of the average shear stress. Okay, 1.5 times of the average shear stress. Similarly, we have a maximum shear stress of 1.5 times of the average shear stress. Okay, so similarly, if we use this equation, then we can again solve multiple equation, and if we simplify that equation, then we will obtain that f over 2y equals times of d square over 4 minus of y square. Again use this equation, and you can solve multiple equation based on that. Similarly, we can use have a circular section. Again we will use the same formula, just change the value of a and y, put these values, and you will get this equation of f over ei r square minus of y square. Again put these values, then you will get the shear stress value at any given section of y. Similarly we can calculate the maximum value and minimum value when you put y is equals to d by 2, and when we put y equals to 0 you will get the maximum value of stresses, and maximum is 4 over by 3 of the average. And similarly if you use this equation you can solve multiple numerical. Similarly we have I section, T section. In this case the distribution of stress will be in this pattern. Again we will using the same formula. We will see this, if we see the shear stress distribution in the flange, okay, then we simply need to put the value of y bar over here. We know the area of that portion, okay, so just put the values and you will get the result, this equation. So that is the distribution in the upper flange. Similarly for at the upper flange and at the down at the lower edge, these two formulas we get. Similarly this is the shear distribution in the wave, okay, and simultaneously put those values of a and y bar and you will get this equation, okay. And again if you put the values of y and d, then you can get the any values in the wave case, whatever the shear stress value will be there, okay. Similarly we will also solve for the T section and I section. On all everything is based on that simple formula. Similarly in the case of T, the shear stress distribution will be like this, and you can obtain same result if you follow the case of the I section, okay. So that was the third unit, and in the next video we will start our fourth unit, okay.